Hello everyone, so this is my continuation to my first lecture which I have uploaded already. So if you haven't watched that lecture, so you have to watch that lecture, so otherwise it will be difficult to understand this. So so this is let's say repeat some part of that lecture. I will repeat some part of the lecture in this lecture. So what I am going to what I have described earlier is that basically what is Monte Carlo integration and how to do the Monte Carlo integration and how that leads to a Gaussian, and using the central limit theorem how to find the error, and which is the basically order of 1 by n to the power half. So and also when it is better to use Monte Carlo integration rather than some deterministic method like trapezoidal method or Simpson method and other deterministic method. So that I have already described. So what I am going to do in this lecture is basically I am going to show you the code and how the error varies. So that I'm going to show you today. So let's do that. So to do Monte Carlo integration, you have to generate in random points xi in problem space, and which is basically the fx, y is equal to fx, and you have to substitute the value of xi in that function. You have to calculate the function value using that function, that is basically f of I, which is basically f of xi. And your expectation of f, which is the average of f, is basically 1 by n sum over I is equal to 1 to n f of I, and expectation of f square is basically 1 by n sum over I is equal to 1 to n f I square. And according to the central limit theorem, for large n the expectation of f will approach a true value f bar, and more precisely the distribution of that expectation of f is basically a Gaussian. So it will have a mean around that f bar, and it will have a variance sigma, and the sigma square is basically expectation of f square minus expectation of f whole square by n minus 1. So and sigma is basically root over of that thing. So as you can see, sigma is basically the width of that Gaussian, and that is basically the error. So as you can see, sigma varies as for large n, it varies as 1 by n to the power half, so root over of that thing. So that sigma will vary as 1 by n to the power half. Right. So that is basically using the central limit theorem you can prove that thing, and I have already proved in my earlier lecture in the central limit theorem. So I have uploaded a lecture on central limit theorem and how it leads to a Gaussian, that I have already described in that lecture. So if you haven't watched that video, you can go through my channel and you can watch that video. So here I am going to show you the code how to calculate the Monte Carlo integration, and how to calculate the expectation of a function and expectation of f square, and how it approaches to a Gaussian. Right. So now let's go through the code. So I have already written the code. So I am just going to show you that code. So which is basically, let's say I want to generate 10,000 random points, and so I am going to generate 10,000 random points. So so I will generate such 10,000 random points 10,000 times. So that is basically the n iter. So I will iterate that 10,000 random points 10,000 times. So if you give it like 1000, so you will generate 10,000 random number 1000 times. So right. So that is basically needed for your histogram data. So to plot a histogram is basically the probability distribution of that expectation of f. So firstly I will open a file data.dat in write mode, and so I will initialize sigma square, which is basically 0.0, and sample mean, which is basically 0.0. So mean and sigma square I have initialized to 0. Now I am creating a do loop which is basically with the index j, which goes from 1 to n iter. So here I have 10,000 ensemble. So we have 10,000 ensemble, right? So we will generate 10,000 random number 10,000 times, right? So that's why why we are doing this, because we want to have a histogram of the data. So if you have 10,000 data, that will be a good histogram, right? So if you have lesser number of points, so the histogram will be not so good. So this process, so firstly for integration I will be generate 10,000 points, and I will do the integration 10,000 times, because as you know that it is a stochastic process which is basically by calling a random number. So every time you call a random number, that random number will give you a different number rather than the previous one. So that's why I will be doing it 10,000 times. So that will give me 10,000 so that will give me 10,000 different random numbers, and that every result for each iteration, let's say for first iteration the 10,000 random numbers gives me some result, and the second iteration the 10,000 random number gives me another result. So that result I will collect and I will plot the histogram of that result. So that's the main motto of this code. So I will do this generation of 10,000 random points 10,000 times. So that is this loop j is equal to 1 to n iter. So I will do this loop 10,000 times, and I initialize sum to be 0.0 d0 and sum square to be 0.0 d0. First one is basically for saving the average value of the function, and sum square is basically for the saving the square of that function. Now what I will do is basically I which is a variable which is going from 1 to n, that is basically the 10,000 points, and I will call a random number ri. Ri is a real type of variable with dimension n. So I will call the random number and I will initialize p as some ri. I will assign p of the value ri, and I will add the value of f of p to sum. So sum will collect all the value of the function, and sum square will collect the square of the function, right, in every for all such I, and I have already defined the function fx to be 1 plus x squared. So here, and if you want to use that function inside your program, you have to just write real 8 external f. So that will use the function. So in this part I am basically calculating the integration. So this is basically for the average of f and data collection for average of f, and this is basically for data collection for square of the average of fx. So now what I am going to do is basically sum by n, so which is basically the definition of the average. So what is the definition of the average? I have already described. So it is basically 1 by n sum over I is equal to 1 to n fi. So this part I have already done, sum over I is equal to 1 to n fi. So as you can see, so that sum is already done, but the division of n is happening here. So I am dividing by n, and also sum square I am also dividing it by n, and sigma square is basically, which I have assigned 0 here. So sigma square is basically sigma square plus sum square minus sum and whole square. So that means this basically the average quantity, and this is basically the expectation of f square. So as you know, the sigma square is basically sum square, means the expectation value of the f square minus expectation of f whole square by n minus 1, right? So from this definition, I am just using the definition or nothing else. So this is the definition of sigma square. So that is basically expectation of f square minus expectation of f whole square. So that is, in our case, is basically sum square, and this is basically sum whole square, and this by n minus 1. So that I am doing. So that is basically, so I am saving the data in sigma square. Now sample mean is basically sample mean plus sum. So I am saving the average in the variable sample mean. So now I am writing that sum and sum square in a file, in that file. For each such j, I am saving that sum and sum square. And now lastly I am printing the final sigma and final sample mean. So that I will compare with that fitting. From fitting I will get some values of that sigma and sample mean, and from the generated data which I am generating here, so I will plot a histogram, and from that also I will get a sigma and sample mean. So I will compare that two value, and you will see that these two values are equal basically. So now let's do that. So what I will do, so this in the file, so sum, which is basically the average of that function. So here I am dividing, so that's why it becomes the average of the function, and sum square, which is the expectation of f square, right? So this is basically the expectation of f square, that I am just writing in a file. And lastly, after exiting two of the loop, so I am just printing the final sigma of that of this program and sample mean of the function, right? So that I am doing. So let's run the code and let's see what happens. So let's open the terminal. Okay, so now let's write gprotran minus o3 will make your program faster, run faster, compilation will be faster. So mc underscore this thing and dot slash a dot out. So it will take some time. So as you can see, my sample sigma is basically 2.90 into 10 to the power minus 3. So that is basically 0.0029 something. So there will be 0.002 something, and your sample mean is basically 1.333 something. So these two value you have to remember, and then I will compare these two value from your from the fitting using Gnuplot. So if you don't know how to fit in Gnuplot, so I have already uploaded a lecture in my Gnuplot lecture series, how to fit a function, so that you can watch if you haven't if you don't know that how to fit a function in Gnuplot. So that will obviously help you to understand this fitting. So now I have written a code histogram how to generate. So also I have uploaded a lecture on how to plot a histogram in Gnuplot, so that you can see in my YouTube channel. And also here I am writing so here I have written a code for histogram generation. So I have already uploaded that code in my previous videos, how to plot a histogram or how to plot histogram in Fortran, how to generate the histogram data in Fortran. So this code I have already described in my previous lecture, how to to generate histogram data. So what you have to do is basically in Fortran you have to write a code, and this code will help you to generate the data of your histogram. So I just run that code, and here I am in that code I am using that data.dat which I have already saved, and it will generate a data for histogram data in the file hist.dat, and firstly it will read the data, and then nextly it will calculate the maximum value of the data points and minimum value of the data points, and then it will just do the job to calculate how to calculate histogram using the binning and like all the things. So that I have already described. If you haven't watched that video, please go through my channel and you will understand how it is working. So let's run that code. So histogram.f90 and ./a.out. So now I have the data for, as you can see, I have the data for this hist.dat, which is basically the histogram data, and now I want to feed that function using Gnuplot. So I have already written a script in Gnuplot. So also I have uploaded a video on how to write a script in Gnuplot, so that you can see if you are needed with this video. So you can watch that video. So there I have uploaded that thing, that how to write a script in Gnuplot and also how to fit a function. So here I have defined the fitting function to be fx equal to 1 by square root of 2 pi b square. So b is basically my sigma, and exponential of minus x minus a whole square by 2b square. So a is basically the true value of that function, and true value of the average, and b is basically the sigma. So that's so this is basically this function. So this function is, so a is x is basically expression of f, and which I have the generated data using the histogram.f90 file. So that data I have. So I want to know that f bar, true mean and sigma. So this I am defining as, I think, a, and b I think I have defined as sigma. So this the function, and now I am fit fx hist.dat via a and b. So it will fit the data of the histogram, and it will print the value of a and b, and nextly it will plot the function, the histogram data generated, the data for histogram and also the fitting data. So let's I have already generated the hist.dat, so I just have to load the code in the Gnuplot. So just type load plot fit.gnu. So here you go. So as you can see, this is exactly a Gaussian, and it is also matching with our fitting parameter. So what are the fitting parameters here we are getting? So as you can see, it is basically 0.0030 something. So here also you are getting so here also you are getting 2.98 into the power minus 3, which is basically 0.003. So that is the power of that coding. So and you can see that your mean is basically 1.33 sample mean. Here also your mean sample mean is basically 1.33. So as you can see, this is a perfect match. So this is a perfect match. So now and the graphs are also matching, so exactly matching. So now you can do one thing, you can play with this value. Let's say that code MC integration, if you decrease, let's say, the number of times you generate doing the integration, let's say 1000 times you are doing. So earlier we are doing for 10,000 times, let's do it for 1000 times. So then if you run this code, so you can see that there will be okay, and you have to use this, sorry, and you have to write 1000, because now we have 1000 point. So now if you write the histogram.f90./a.out. so now in Gnuplot, if you now load that value, so now the sample mean is basically 2.98 into same sample mean, and that value is 1.333. Now, so as you can see here, okay, so let's do it. So here now, as you can see, the match is not exactly perfectly with that histogram data. So the blue one is the histogram data, and the red curve is from fitting. So as you can see, the bean size is also increases. So earlier the bean size is very small, so here the bean size also increases, and the fitting is not so much good. So and also you can see that value is 0.0031, which is quite large from this 0.00298. So now let's increase the value further, so it will take some time. So if you make it let's say 20,000, let's do it. It will, I think it will take some time because of that random number generation. So let's use Deterministic minus 03, this thing, ./0.out. Let's wait. Okay, it's quite fast. So now so in histogram.f90 you have to make it 20,000, and you have to run that code. Okay, good. So next you just load that thing. So here, as you can, the value is basically 0.0029, which is basically quite close to that value. So here it is, the sample mean is basically 1.3345, and the mu is basically 0.0029. So as you can see, this value is 2.98 into the power minus 3, which is basically 0.0029, and here also 1.333. So it is quite good actually. Now let's see the plot. So as you can see, it is very good match with the numerically generated data and the fitting parameters. So this is perfectly Gaussian, and I can also approximate the mean from here also. This is basically 1.333 something, and don't confuse with that minus sign, because in the power of that exponential, it is basically x minus mu is whole square. So it is, as it is whole square, so it is giving that minus value. So as we are squaring, the value will be the same. So if you pin the square value, so it will be the same. So we have to pin basically the square of the sigma square. So if you pin the sigma square, then it will be the most of the same sign, because it is basically printing the negative sign. So if you just modify that thing, so you can modify it here. So let's say plot fig.gnu, so just pin b square, let's say, which is basically the sigma square, and also here that in the code mc underscore this thing, here if you make it square, sigma square, so we don't need the square of that thing, we'll be just needing this thing. Okay, so now just run it. Input run minus 03 mc underscore this, and then this. Okay, so far so good. So this is the square value, basically 0.00888 something, and the maple mean is 1.33. Now if you run the histogram.f90, okay, now if you plot that thing, so now our sigma, that's basically sigma square. So I have forgot to written that in my code. So that's basically sigma square is basically this thing. So now if you load that thing, so as you can see, this is basically 8.922 into the power minus 6, and here also it is 8.88 into 10 to the power minus 6. So almost of the same number, of the same order. So order of magnitude is basically same, and the numbers differs basically. So now if you see the plot, so there will be a perfect match. So now if you increase in further and further, so you can see that the plot will be exactly matching with each other. So if you make it 50,000, I think it will take some time, but you can see that will be a perfect match. So okay, before doing that, let's make it sigma square. That will be confusing. Sigma star sigma, let's say. So let's do that thing. Okay, I think it will take some time, but let's see. If it take much time, then okay, fine. So now you have to make that in histogram folder, histogram file. You have to make it 50,000, because now we have 50,000 data points, right? So okay, histogram. Okay, let's see. Now just, so now as you can see, the value is 8.88 into 10 to the power minus 6 for sigma square. Now if you open Gnuplot and load that thing, so the value is basically 8.85 into 10 to the power minus 6. So almost of the same number, and you can see that match is exactly perfect. So it is exactly matching with our training parameter. So that is the same, basically the same. That is due to basically the central limit theorem. So this is the power of MC integration. So as you can see, the error is of the order of 1 by n to the power half, independent of the dimension of the integration. So here I am using only one dimension. So if you increase the dimension, your MC will be much more better rather than the lower dimension. So the main point from this, main relation from this thing is basically your expectation of f of a function will approach for Monte Carlo integration will approach to a Gaussian distribution eventually if your n is so large. And also one thing that for lower dimension, your deterministic method like trapezoidal method, Simpson 1/3, Simpson 3/8, that methods are very good, but Monte Carlo methods is not very good in lower dimension. But when you are in higher dimension, d greater than equal to 8, which I have put in my first lecture on that series. So if you've seen that thing, you will understand that if d is greater than equal to 8, then your Monte Carlo integration with using the random number generator, so that will take place is in terms of betterment of your error. So your error will be less in that stochastic method, which is the Monte Carlo integration in d greater than equal to 8 dimension. So when your dimension is basically greater than 8, so your Monte Carlo method will be good. So the deterministic, deterministic method means so you are not using any stochasticity in that method. So you are just making some equidistant grid in your method. Just say if you have a lower limit a and upper limit b, so you are just making some equidistant grid. You are just dividing your interval in sub intervals, and you are just doing the integration. But it means in stochastic method you are using some random number generator like MC integration, Monte Carlo integration. So you are using some random number generator which is basically stochastic. So every time you will be doing the integration, so you'll be getting some number close to the actual value, but not exactly the same number because of that stochasticity. So that is the power of that Monte Carlo integration when you are in higher dimension. So thank you for watching this video. If you are new to my channel, please subscribe to my channel. So I'll be uploading more videos on Monte Carlo integration and other things, and I have also uploaded many lectures on physics through computation. There you can watch simple harmonic oscillation, like a coin, all in also in Monte Carlo series I have uploaded coin tossing phenomena, Buffon's needle, and also the particle diffusion, other things. So if you haven't gone through my channel, please go through my channel, and I think you'll be having fun. So thank you.